All right, guys, let's look at type 2 problems. So, in a type 2 problem, we've got a few things going on. This is when our projectile, I did not spell that right, is launched horizontally from unlevel ground. Because of that, our max height is equal to our launch height. Because we're starting off high up in the air, and we're not launching it any further up. We're launching it out and across. Also, if we're launching it horizontally, our initial y component is going to be 0 meters per second because it's going horizontally, and a horizontal line has no y. A horizontal vector has no y component. That y component of a horizontal vector is 0. So without further ado, let's look at this type 1 problem. Or type 2 problem. Maybe? Oh, I have the type 2 problem over here. A stunt car is being used in a movie scene. The stunt car will drive off a 74.7 meter high cliff with an initial horizontal speed of 55 kilometers per hour. To film this stunt, the director needs to know how long the car will be in free fall and how far from the base of the cliff the stunt car will land. Also determine the stunt car's final velocity. So as with anything, the first step we're going to take is to draw a diagram. So we need to draw a diagram of what we know. So we know the stunt car is going to drive off the edge of a cliff, and that cliff is 74.7 meters high. And this little car, vroom vroom, is going to drive right off the edge of this. And that horizontal speed is 55 kilometers per hour. So that's not going to do us much good because it's in kilometers per hour and our height is in meters. And we usually work in meters per second. So let's go ahead and convert that. And I'm going to move this really quick so I have some more room to write and for you to see. So off here to the side somewhere, I'm just going to say it's going 55 kilometers in 1 hour. So in 1 kilometer, I have 1,000 meters. And in every 3,600 seconds, I have 1 hour. So I'm going to get that my initial velocity when it goes off that cliff is 15.27 meters per second. So there's my initial velocity. Step number 2, I want to define my positives and negatives. So I'm going to draw my little compass up here, and I'm going to say positive, positive, negative, negative. So my car is going to launch off this cliff, and it's going to land over here somewhere. So the director wants to know where it's going to land. It wants to know how long. And it wants to know its final velocity. So let's get to work. After we define our positives and negatives, we want to make our variable columns. I'm going to try to focus this again really quick because it's bugging me. All right, so I have my x variables chunk, chunk. And my y variables, on the x-axis, I have my range. I have my horizontal velocity and change in time. On my y variables, I have my change in displacement, or my vertical displacement. I have my initial y velocity. I have my final y velocity. I have my acceleration. And I have my change in time. I'm going to fill in what I can figure out from what's available on this graph. Acceleration pulls down, so it's going to be negative 9.8 meters per second squared. My change in displacement, or my displacement on the vertical axis, it's going to fall 74.7 meters. It's not going to ever get any higher than that because it didn't launch upward, it launched outward. So that max height is also my final vertical change in displacement. All right, and our initial velocity was 15.27 meters per second. And usually we would divide that into an x and a y. But there's no y if it's horizontal. So my initial y velocity is 0 meters per second, which means that my horizontal velocity is 15.27 meters per second. And up here, I said I was looking for my range, my change in time, and my final velocity. And those are the three variables I have empty here. So I've labeled everything I can. So after that, I'm going to look for my change in time. And I'm going to use the same equation I used last time. So my displacement is equal to my initial velocity, change in time, plus 1/2 acceleration, change in time squared. And I don't have initial and final components on the x-axis, so this is always going to go with my y variables here. All right. So now that I have my kinematics equation, we're going to plug in what we know. The first one is our displacement vertically. It's 74.7 meters, but it's 74.7 meters down. So I'm going to make sure this number is a negative. That's super important. Please watch your signs with your directions. My initial velocity vertically was 0 times my change in time plus 1/2. Acceleration is negative 9.8 meters per second squared. Change in time squared. So I'm going to get negative 74.7 meters. That's all going to cancel out. Equals negative 4.9 meters per second squared. Change in time squared. I'm going to divide out this negative 4.9 meters per second squared. My meters will cancel. I'll get 15.245 seconds squared equals change in time squared. I'll take the square root of both. So my change in time will be 3.90 seconds. We can throw out that negative because we don't have negative time. So I'll take that 3.9 seconds and I'll come up here to change in time and I will plug it in. So my next step is going to be to solve for my range. So velocity equals my displacement of x over my change in time. So 15.27 meters per second from right here is equal to my range over my change in time was 3.90 seconds. So my range is going to be 59.65 meters. I can plug that in up here. All right. I've got this. I've got this. All I have left is this. So I am looking in step 6 for final velocity. All right. I will use my final velocity squared is equal to my initial velocity squared plus 2 acceleration displacements. So I have my final velocity on y squared is equal to my initial y velocity squared plus 2 accelerations displacements of y. This is what I'm looking for. I'm looking for that final velocity. My initial y velocity was 0. Oh, that squared is a little off. Plus 2 times my acceleration was negative 9.8 meters per second squared. My vertical displacement was 74.7 meters down. So this is going to be negative 74.7 meters. I'm going to do my math here. All right, so some of y'all might wonder why I chose the negative when I took this square root. And I chose the negative because the negative is down. And if we look at our problem up here, our final velocity isn't up in the air down here. Our final velocity is heading down towards the ground. So we're going to use the negative there. All right? But that's not all. That's not the only component of final velocity we need. We also need to know, or that's the y component of the final velocity. We need to know the total final velocity. So we're going to create a right triangle. So it's coming down and it hits the ground. Here's the ground. We just said that this final component on the y-axis was 38.13 meters per second. Our horizontal velocity never changes, so it's 15.27 meters per second. And this is what I'm actually looking for. So a squared plus b squared equals c squared. So 15.27 meters per second squared plus 38.13 meters per second squared is equal to this final velocity squared. So this final velocity is going to come out to be 41.07 meters per second. Great. What is this angle? Because velocity has to have direction. So right now all we have is speed. We need to have a direction to go with it. And we can't just copy it from the beginning like we did in type 1 because it's launching horizontally. So we're going to have to use those trig ratios. So the tangent of theta is equal to adjacent over opposite opposite over adjacent. I'm so sorry. All right, so my tangent of theta is equal to negative 38.13 meters per second over 15.27 meters per second. Theta is going to be 68.2 degrees. So when I add those two together, my total final velocity is 41.07 meters per second, 68.2 degrees below the hill. So all I have left to do is to write my therefore statement for this problem. My therefore statement for this problem would say, therefore, the stunt car's time of flight, which was the first thing we were looking for, is 3.90 seconds. It will land approximately 6.0 times 10 to the first meters away, and its final velocity is 41.07 meters per second, 68.2 degrees below the hill.